Now this week we are starting the lecture number 2, and entitled it Moving Blindly and Seeing the Light. I have two goals today, is introduce you to our coordinate, celestial coordinate. So I mentioned last week that it's important to be able to spot an object in the sky, and I already told you that the way we're doing locally, just looking up and measuring the azimuth and the altitude, those system of coordinates, works only locally, and so it's not very practical for astronomers. So we had to introduce another system. And I also described the properties of light. So I already mentioned that in the past 2 weeks. Light is the only thing that astronomers cares about, because this is all the information we get from celestial sources, from stars, galaxies, planets, is coming to us through lights. It's the only way we can have access to information. We can't bring things apart from very close by, nearby objects like the moon or even Mars, where we can send probes there and do analysis directly on the ground. We'll come back on that in a few weeks. But otherwise, apart from those close bodies, we can't really go there or bring things from there. It's too far away. So we just have to rely on light. And actually light is a very wonderful thing and has lots of very, 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 very useful properties that I will describe today. And we'll come back all around again about the properties of light throughout the full series of lectures, because this is, once again, the only way we can observe our universe. So I come back to the notion of celestial sphere we defined last week. Remember, what we do is we project all the stars around us on a sphere around us. So it's not a physical sphere, it's not something that exists, it's just a projection. Object looks at the same distance from us, but they may be at different distances. So if you look at constellations, remember the example I gave with Orion, you look at the constellation, it looks like a drawing on the sky, but in reality those different stars may be very distant one from the other. So we just project it on what we call the celestial sphere. And we define several things on our celestial sphere. The north celestial pole, that is corresponding to the projection of the axis of rotation of Earth on itself, on that sphere. And near south, you have the south celestial pole. And then, corresponding to our equator, you have the celestial equator projected on that sphere. And of course, if you are at a given position on Earth, so this is you there in the US, your zenith, the point that is the highest on your head, in the sky, doesn't correspond to the North Celestial Pole, unless you are at the North Pole. Okay? We'll define your north to the direction of the North Celestial Pole, but the North Celestial Pole will be a bit lower on the sky. So your position, what you see in the sky, will depend on where you are on Earth. If you're there in Australia, you won't see at all the same sky. So what we have done, and we have seen so far, is one way we can do to to avoid this problem of positions on Earth, is to define constellation and asterisms. So those constellations are defined by zone. So there are 88 areas on the celestial sphere, which comprise different stars, and you can use these positions, exactly like countries, to define where the object you want to study is. So this celestial sphere is divided in constellations, and there is a very notable thing on the celestial sphere, is what we call the ecliptic, which is the path on the sun, apparent path of the sun on that celestial sphere. And remember, the ecliptic doesn't correspond to the celestial equator due to the tilted axis of rotation of the Earth. So there is an angle of 23.5 degrees there. And when the ecliptic is crossing the celestial equator, so it's eastward, this is called the vernal equinox, and the other way around, it's called the autumn equinox. And when the sun is at the top, exactly at 23.5 degrees here, up on the celestial sphere, this is the summer solstice, and when it's down there, minus 23.5, this is the winter solstice. So the purpose of a coordinate system is first to locate stars, galaxies, or other objects in the sky. If I observe an interesting object and I want to tell my colleagues, oh, look up there, I need to provide them for coordinates. precise coordinates because some of the objects are very, very tiny, very small, and very faint. So we need to have a very precise system. So to locate an object in a space, we saw that last week, how many quantities do you really need? Well, in a three-dimensional world, like we are living in, you need three. X, Y, Z. So you need 3 dimensions. Or you can use another system, which is a 3-dimensional system. It's directions. Okay, which direction? So a degree. And a distance. So you have 1, 2 directions, and the distance, which is the third. So this is what we call the polar coordinate system for physicists and mathematicians here. This is something you are used to. So when you don't care about the distance, which is the case of celestial sphere, or the case of the position on Earth, you end up with only 2 quantities. Okay? An angle there and an angle there. You just have to define a 0 point, where is your 0, and then from that you're set up. And something you're very familiar with, this is the coordinate system we're using on Earth. All the GPS will give you a longitude and a latitude. So if you want to define the position of Roma, you just need the latitude and the longitude coordinates, and you will find it on the sphere. So it's defined, you need a 0 point, so you need to define what we call the prime meridian, which is called Greenwich. Greenwich being a village in England. So this 0 point, prime meridian, go through Greenwich, so it's the longitude 0. And then the second one is the equator, which is defining the latitude 0. So here you had 0, 0, it's exactly there. So now I'm telling you that I'm going longitude 12 degrees east, so I'm going up there, and latitude 42 degrees north up there, and you find Rome. So on the sky we're doing exactly the same thing. I showed you last week. We can use the horizon as our 0 point, and we have to define one latitude. So what we're using is the north. So the meridian is defined up to the north, so you find celestial north pole, and it's indicating you the north, and the south pole if you're in the south. So you have a north-south axis. So the horizon is your reference frame, and the altitude is the height above the horizon. So it's going from 0 to 90, and back to 0. So, okay. And what we call so it's called the altitude. And what we call the azimuth is the angle measured east along horizon from north point. So you take 0 point here, and you go 90 degree, 180 degree, 270 degrees, 360 degrees. So now, if I want to look at this star here, I just give an altitude of 60 degrees and an azimuth of 135 degrees. And I know where it is on the sky. So we saw that last week. So the advantage is really easy to understand. And if you go outside with some astronomers, amateur astronomers, this is the way you will use to explain how to look at these stars. To look at these stars, these are the coordinates, and you can point your telescope very easily. The problem, I mentioned that already, is that at different position on Earth, the same object has different coordinates. Of course, it's relative to your position on Earth. So if I take at a given time the coordinates of one star when I observe it from Taiwan, and I tell one of my friends in Russia to look at it, the coordinates on the sky will be totally different. And even more worryingly is at different time, different period of the year, because the rotation of the Earth on its axis and the revolution of the Earth around the Sun, so even during one night, these coordinates would change as well. If I look at the sky in summer, it's totally different from the sky I see in winter. You don't see the same stars. So at different time, the same object, we also have different coordinates. So in the horizon system, or ALTAS system, the coordinates change all the time, which is very not practical. So just to illustrate that, okay, this is the celestial sphere. So you have the north celestial pole, the celestial equator, the south celestial pole, and your local system is defined by your horizon here and your zenith. And you understand easily that in the US or in Europe, you won't have the same zenith. So the coordinates would be totally different. So this, your local sky, depends on where you are on Earth, which is not practical. So we have to define another system that is independent of where we are on Earth. So we need to define some 0 points. And the system, the reference frame, is the celestial sphere. Once again, the celestial sphere is defined from North Pole, celestial equator, and South Pole, and doesn't change. It's always the same. North Pole is always the same. Modulo the 26,000 years of wobbling I explained a few minutes ago, but globally, within 1,000 years, the North Pole is always the same. So, what you have is you need to define the North Pole, and you need to define an horizon. So your horizon will be the celestial equator. And you need to define a 0 point on your celestial equator. So we define it as the vernal equinox. So this is the position of the sun when it crosses the celestial equator from south to north. So you remember the celestial equator. Let's say that the ecliptic is something like that. And when the sun, the path of the sun is crossing the celestial equator, corresponding roughly around the 21st of March, then this is what we call the vernal equinox. Then we introduce what we call declination. This is the minimum angular distance from the position of a celestial body and the celestial equator. So this position here, on that direction, exactly like our latitudes. So this defined by degrees on the sky. So it goes to minus 90 to plus 90, minus 90 to plus 90. Then there is the right ascension. So this is the eastward angle from the vernal equinox to the intersection of the object. Our circle within the equator. So that means this is the 0 point. So exactly like we did with the horizon, we define a degree there. So you go from 0 to 360 like that. So if I have an object, let's say here, I go from 0 to the right ascension on the celestial sphere, and then up to the declination. So with two coordinate system, I know the position on the sky. And I'll come back on that. Astronomers are a pain. I had a hard time when I was at your place and as a student to understand why the system has to be so complicated. But historically, we are not defining in degrees. It would be very practical, but it's not the way we're doing it. We're using angles, hour angles actually. So 1 hour angle corresponds to 15 degrees. So instead of defining from 0 to 360, we define from 0 hours to 24 hours. So 1 hour corresponds to 15 degrees. So the right ascension is defined in hour of angles. And of course you use hours, so you will use what we call arc minutes. So it's 1/16 of 1 hour. And arc second, 1/16 of 1 arc minute. I'll come back on that in a minute. But to make things even more worse, we use hours for the right ascension, but we use degrees for declination, from minus 90 to plus 90. But we use minutes of degrees and second of degrees as well. So I'll come back, I'll explain to you with an example. So usually we will write angles in that way. 35 degrees, 27 arc minutes, 35 arc seconds. Why are we using such complicated things? That's because actually we are measuring distances across the sky with angles. If you look distances between two objects, this object and this object, it's easier to just define an angle. So we will say this object is 5 degrees away from the other, because it makes more sense for us as astronomers. Okay, so let's go back to those definitions. So this is what we call the celestial or equatorial coordinate system. So it's a system in which the coordinates of an object does not change. It's fixed on the celestial sphere, which is exactly what we want. So we define the vernal equinox as the 0 point. This is the ecliptic plane. This is the celestial equator. This is the North Pole and the South Pole. And if I want to look at this object here, which is for instance the star Vega, then I just look at its declination, so how high it is compared to the celestial equator, 30 plus 38 degrees and 44 arc minutes. Okay, it's there. And then I look at its right ascension from 0 to plus 18 hours, 35.2 minutes. So it's exactly like the longitude and latitude system on Earth. You have right ascension and declination, what we define as an equatorial system. So the equatorial coordinate system rotates with the Earth, so it's always fixed with time. Okay, it's fixed compared to the rotation of the Earth. So, compared to where you are, so for our local sky, for instance, you have this person here, the astronomer here, have his zenith, opposite to zenith, his horizon. So what you will have to know is where is the position of the north celestial pole, south celestial pole, and celestial equator. And use this to look for the star. So it will use, this is for instance the vernal equinox point, it will look for the right ascension and declination, and will give it the coordinate of the star in the sky. And actually, if he knows what time it is, where he is on Earth, he can convert it to his local sky. So you can do a conversion, which is dependent of time and position on Earth, from the local system, local sky, to the equatorial coordinate system. Astronomers, we never use anymore the local sky. We just use the automatically the equatorial coordinate systems. Actually, your telescopes, nowadays all the telescopes we're using, they are automatically set up in that system. You don't even have to do the conversion, because the telescope, the computer knows where it is and what time it is, so it's doing automatically the conversion. So if you go to a professional telescope, you ask your telescope operator, you just give him the coordinates of the object in this system, and the computer will do all the calculation for you and point to the right direction. So declination are going from 0 to 90 degrees and 0 to minus 90 degrees. So minus 90 correspond to the south celestial pole, and plus 90 correspond to the north celestial pole. So here we have the declination of 60 degrees, 30 degrees. Declination of 0 degrees corresponding to the celestial equator. So declination can be positive and negative. And the right ascension, so you can imagine that it's an imaginary line that connects the celestial pole from north to south. Then you look for where the vernal equinox is, and you look for where this line crossing the object of interest from north to south is crossing the celestial equator, and this angle here gives you the right ascension. And once again, it's not defined in 360 degrees. We're using hours, minutes, and seconds. So it's going from 0 hours to 24 hours. So for instance, Andromeda galaxy, the galaxy of Andromeda, which is the closer galaxy to us, is closer big galaxy to us, has a right ascension of 0 hours, 42 minutes, 44 seconds, and a declination of plus 41 degrees, 16 arc minutes, 9 arc seconds. One advantage of the era system, of the equatorial system, is that stars with larger right ascension will rise later. So if you know that your twilight corresponds to a given array, let's say 22 hours, and you want to observe an object that is 4 hours, in an array of 4 hours, I mean you have to wait for 6 hours to see it coming up. So if it's the midnight now, and it's 22 hours of the sky, you won't see your object before 6 hours in the morning. So that's why we're using this kind of system. It's very practical for us. So this array will correspond actually to the time you have to wait to have your object coming up. So, well, once again, historically we're using this very complicated system of celestial coordinate in hours and degrees. More and more commonly, with the advent of database and computer systems, we are moving towards degrees, decimal degrees. However, astronomers still like to use this system. So this is the way you will convert from the hour, minute, second, and degrees, arc minute, arc second system to a decimal degree system. So for the array, you start from 0, 90, 180, 270, and 360 degrees, which correspond to 0 hours, 6 hours, 12 hours, 18 hours, 24 hours. So actually, if you have seen Top Gun, you're probably very young, but it's still going very often on the TV with Tom Cruise. So when they're piloting their jets and they want to spot on where's the enemy, they're saying, oh, it's 6 hours. So you're 6 hours, it's over there. 12 hours, it's behind me. 18 hours. So this is a way we're using. Or when I was younger and not married yet, and drinking coffee in France with my friends, and we spot on a beautiful girl, we're saying, girls at 4 hours. Okay? This is the way. It's exactly the same way. You just imagine the clock and it's corresponding to it from 0 to 24. So 1 hour corresponds to 15 degrees. Then if you want to convert right ascension, 18 hours, 36 minutes, 56.3 seconds, then you have to do 18 plus 36 divided by 60 plus 56.3 divided by 3,600, multiplied by 15, and gives you to the position in degrees, decimal degrees. And for DEC, this is already in degrees, so you don't need to multiply by 15, but you still have to do a conversion from arc minutes and arc second to degrees. I know it's complicated. It's not really a problem, I'm used to it. Actually, I remember now the numbers of different objects with this coordinate system because I'm using it in the past 15 years. But once again, more and more we're moving to that decimal system because with computers it's easy to deal with. Now, we have this coordinate system, so we can start spotting different objects on our sky. However, some of our objects, they are not fixed on the celestial sphere. Their coordinates on the celestial sphere change. This is the case of the Sun, this is the case of the Moon, and this is the case of the planets. They are not fixed on the celestial sphere. Why?
Too close to us.
Exactly. They are very close to us, so they are orbiting around the Sun as well. So stars are very far away, and actually you'll see later that some stars are what we call proper motion. They're actually moving slightly. But those objects that are very close to us, they move apparently in the sky. So it's something that we know since a very long time. So how you can spot, for instance, the coordinate of the Sun at a given time. So remember that the Earth is tilted on its axis. So the line through the stellar pole is not perpendicular to the plane of ecliptic or the plane of ecliptic itself. There is an angle of 23.5 degrees. So that first of all tells you that the DEC will change with time. And actually, you can, by definition, the declination of the Sun on the celestial sphere on March 21st is 0, and it will reach 23.5 degrees in June for the solstice of summer. Then it go down to 0 for the equinox of autumn, and then go down to minus 23.5 for the solstice of winter, and back again. And for the array system, well, it's going from 0 to 24 hours, so it's changing with time, with seasons. So in spring it's 0 hours, in summer it will be 6 hours, in fall it will be 12 hours, in winter it will be 18 hours, and back to 0. So the position of the Sun is changing with time on the sky. But we know it's very easy to define, from the definition, it's very easy to spot where the Sun is according to the time of the year. So for instance, around the 21st of March, this is the spring equinox, by definition, the right ascension and declination of the Sun is 0, 0. So 1 month later, it will be 2 hours plus 12 degrees, then 4 hours, 20 degrees, and then in summer, it will reach 6 hours plus 23.5 degrees. Then array will keep increasing, while DEC will go back to 0 up to September, and then go to the negatives when you reach the winter solstice. So it will be 18 hours minus 23.5 degrees, and then you go back to 0, 0. So if this wants to work, this is a parent position with the dates here of the Sun on our sky. So this is the fixed sky, celestial sphere. Here you have the celestial equator, and this is the ecliptic of the Sun. So those stars are fixed, but the Sun, with time, is changing its position on the celestial sphere. This is where the spring equinox here, summer solstice, vernal equinox, winter solstice. So we have this with the Sun. You can imagine that the Moon will have also a given path. It's slightly more complicated because the Moon is orbiting the Earth. And planets also will have a very defined path on the sky. So that's why we can predict largely in advance where a planet will be, because we know exactly its orbits. I'll come back on that when we'll talk about planets. So in our coordinate system, the ecliptic is the reference circle, the ecliptic plane, and we have a reference point, which is the vernal equinox. This is what we call the ecliptic system. There are many other coordinate systems than the equatorial system. There is the ecliptic coordinates, where the reference circle is the ecliptic plane. So instead of using the equatorial plane, you can use the ecliptic plane. So then the declination of the sun will be always the same, but the area will change, but the declination of the sun will be always the same. The problem with that kind of system is that then the stars will move, but it's one way of doing it. Another way is to refer to the galaxy, our own galaxy. So you can take our galactic plane. So we'll come back when you talk about galaxies, but you can use the galactic plane, so the Milky Way, the position of the Milky Way in the sky as a reference, and as a reference point, the direction of the center of the galaxy, for instance, and define a system like that. Once again, this is a problem because then all the other objects would move. But some people will like to use these kind of systems. Commonly, nowadays, there is no one is really using any of those systems. We all use the Arabic. This is the most common way of doing astronomy. And of course, all those systems can be connecting to each other, and you need to go for a conversion, which are quite complicated calculations. So do you have any questions about this kind of coordinate systems? Is it clear? I know it's complicated, I know it's boring, but this is important because this is the way we're spotting our object on the sky. And this is the start of everything. So we're going to move to something that I found it a bit more exciting. This is the properties of light. Light is a wonderful thing. We don't measure the importance of it, but we're using it every day. Ask blind people. It's not really easy to not seeing. So light is a wonderful thing for us, and actually it has many, many, many properties. But I will start with something I mentioned in the first lecture. Remember that behind all this physics, all this jargon, all those mathematical formulae, there is something very important with science, is that it's beautiful. So light has very beautiful properties. So when you're taking pictures of the sky or looking at nature, all this can be explained with science, but never forget that you can take very wonderful pictures. So lots of people like Chen Kwan on the back are doing amateur astronomy, and they are taking very, very beautiful pictures of the sky, and this is usually the first step when you're doing astronomy. Then comes the physics. So remember that. This is a nice picture where you see the light of the sun going through the clouds. So the question is, what is light? It's not an easy answer. It's actually a very complicated domain of physics, and people are still working on it. And there are lots of things like we talk about duality of light. Light is at the same time wave and particles, that kind of things. And it took us a long time to understand it. But the properties of light are known since a very long time. So it's a very long history. One way you can define light is by the fact that it's a radiative energy. It's carrying energy. And you know that because if it's a very sunny day and you lie down in the sun, you will feel very hot. And it's very cloudy, you will feel cold. Yesterday was very hot, it was sunny. Today it's cloudy, it's very cold. So obviously, light is carrying energy. Light is carrying energy, just the demonstration here as well. Okay? The laser is just projecting a light flow, so it's carrying energy. Radiation, heat, if you take convectors, so we don't have that much of this in Taiwan, because usually it's not very cold, but where I'm from, believe me, you need to have radiators at home, convectors. It's radiating heat. It's actually a form of light as well. So light is a radiative energy. Radiation means it's transmitting by waves. So you can measure the energy of the light. You can measure the power of its light, how powerful the energy flow is. So this is the rate of energy flow. The power is the rate of energy flow. And it's measured in unit of watts. So you probably are aware of the system of watts. You know it when you want to change the light bulb of your in your room. You know that 200 watt bulb is generating more light than 100 watts. So this is actually the measure of energy that the light bulb is emitting. We use another system, which is actually the international system. It's joule per second. So joule, it corresponds to calories, something you're probably more used to. Calories, when you want to do a diet, you're counting how many calories you have in your diet. If you follow Weight Watcher, that's what they're doing. But calories is a measure of energy. It's joule, same thing. But here it's the flow of joule. That means the amount of joule or calories you get per second. So 1 watt is 1 joule per second. Another very practical and wonderful property of light is light have different colors. And you all know that, but first because, for instance, this one is green and this one is red. But you know that light is having different colors because of those magnificent rainbows. So when I'm driving every day from Taiyo and to come here, I'm crossing the mountains, and if it has been raining in the morning and it's sunny again, on the motorway you have those wonderful rainbows everywhere. So rainbows are just an expression of the properties of light. That light is coming using different colors. So this variation of colors from blue to red is what we call a spectrum. And actually white light is when all the colors are mixed together. And black is the absence of color. So that's why we have the rainbow. The rainbow is exactly the same problem system that we have when you're projecting white light in a prism. When you're projecting a beam of white light to a prism, due to the property of the glass, then the angle at which the light is emitted is depending of its color. It's depending of its place on the spectrum. And I come back on that. It's depending of its wavelength. So light here in that case can be expressed as a wave. And you see that in that picture, the red part of the light has longer wavelength than the blue. It has shorter wavelength. By wavelengths, I define this distance between the peak here to the peak there. The distance is here is longer than this distance is here. All this is light, okay? It's light with different wavelengths, different energy. So the visible light, the white light that we see, so main part of your bulbs are projecting white light. The sun is projecting yellowish white light, actually it's greenish. So this white light is actually a combination of many different wavelengths of light. So if you project a white light beam into a glass prism, then the reflection at which the red and the blue part of the light will spread through the glass prism will be different. So this angle would change with the wavelength. So then if you do that and you project it on a screen, you will have red to violet. You will have exactly the colors of the rainbow. So red to violet, so through orange, yellow, green, blue, indigo. And actually we come back on that. There are colors that our eye can't see, but they are there. It's called infrared for when you go to redder, and it's called ultraviolet when you go to bluer. So from red to violet correspond to a decreasing wavelength. So lambda is this distance between two peaks of wave of the light. So lambda is higher, longer for red, and it's lower for violet. And it's corresponding also to energy. We say usually that the energy is inversely proportionate to the wavelength. That means that the energy carried by red light is lower than energy carried by a violet light. And this you know that. You know that you need to protect yourself from UV, ultraviolet. You know it's very bad for your skin. So when it's very sunny, you use sun cream or you're using UV protecting sunglasses to protect your eyes. Because the ultraviolet is dangerous for your skin and your eyes. But actually it's dangerous because the energy carried by these wavelengths is far higher than the other energies. Okay? So you can have very nice effects of light. Once again, always coming from the beauty of nature. So this is a very beautiful picture. Once again, I try, as long as I remember to do it, to put a reference to Astronomy Picture of the Day. So refer to the first lecture. There is a website called Astronomy Picture of the Day, and every day they publish a picture taken by astronomer or related to astronomy. So usually when I have pictures in a lecture, I put the date at which it was published on Astronomy Picture of the Day. iPod. So if you want to take that picture, you can just go on the website and download it. So, like I said, we all know those colors from red to violet, the colors of the rainbows, because we can see them. Actually, our eye is tweaked to see those colors. But there are other colors that we can't see. Actually, some animals can see. You know that For instance, cats can see during the night. Actually, cats can see during the night because they can see in the infrared better than us. So it comes down to the discovery of the infrared wavelength. So all come down to that man called William Herschel, Friedrich William Herschel, who was German. Let's say he was doing a lot of things. He was a rich aristocrat, so like these days, back to the 18th or 19th century, all the science was mainly conducted by people that were rich because they have money and they didn't have to work really. So they were spending their time doing fun things. Coming back to physics is actually fun because at this time, main part of the people were doing just for fun. So he was an astronomer. You can see that these are telescope on the backyard here of this picture. On one of the telescope here. He was doing a lot of astronomy. Actually, there is a telescope, space telescope, launched a few years ago. It's called Herschel telescope, after his name. One of the properties of the light I mentioned is the fact that the light has different wavelengths from red to blue. So I mentioned that red has a longer wavelength and blue a shorter wavelength, and also mentioned that it's carrying different energies. So Herschel was interested in relating the colors to the energy. So the way the apparatus is set up was he just put a prism on his window, okay, with a slit. So the light of the sun was going through this prism and it was projecting on his desk. So he had the rainbow from violet to red on his desk, projecting from the sun. Then he designed this apparatus here, which was composed of 3 different thermometers. Okay, thermometer measure temperature, that means energy. So he had 3 different thermometers, 2 for each extreme of his projected light, and 1 there that was for 0 point, okay? Because you want to be independent of the temperature of the room. So it was the reference point, and then 2 measurements of the light. And what he did was first putting those 2 thermometers on the light in the violet, measuring the temperature compared to the temperature of the room, and moving slightly his apparatus for each wavelength. So like that, he had a correspondence of energy, and temperature, and wavelength. So he realized that red was less energetic. The temperature compared to the temperature of the room was slightly higher. But when he was going to the blue, it was going higher and higher. The temperature was going higher and higher. So red carries less energy than blue. And what he did at some point is that he moved this apparatus away from the projected light, so a bit lower. So as seen in this drawing, you see that the end of the thermometer are not on the light anymore. And what he realized is even so he was away from the projected light, there was still a difference between those 2 thermometers and this one. Lower than when it was red, but still a difference. So his conclusions were, well, there's probably some light here with lower energy than red, but my eye can't see it. It's there, I can measure it, but my eyes can't see it. And he called it infrared, for below red. So lower energy than red. And infrared is now very well known, actually. It's one of the wavelengths commonly used. So these are pictures taken using infrared cameras. So if you have seen Predator with Arnold Schwarzenegger, there's this alien coming on Earth and hunting people and hunting Arnie. And at some point in Predator, he's switching and he's having lights, Google lights, and can see forms in this kind of colors. So it's just infrared detectors. It's also used by the militaries to look for people behind walls. So what infrared detects is actually a source of light. And we'll come back in a minute on that. But our body is actually a light bulb. We're emitting light. We're all very bright. So don't believe anyone that's telling you that you're not bright. You're all very bright, but we're all very bright in the infrared. So every source of light is actually emitting light in the infrared. So this is, for instance, a picture of 2 cups, a glass of water, one with hot water, one with cold water. And you see that the hot water is emitting lots of light in the infrared, while the cold water doesn't. And these are the picture of, for instance, a pig and a human here. So you see that the pig is emitting a lot of light in the infrared, also the human. This is a picture of a cat. So cat is emitting less light than the pig, obviously, but you see that his eyes are very, very bright. It's because cat's retina is very sensitive to the infrared. So actually cats can see throughout the night because they can see in infrared. They can detect the prey, they can see the prey if they are emitting light. And if you look at, for instance, a chameleon, here, this is a picture. So this is a human hand, and this is a chameleon. So you all know that chameleon have the properties to change color according to its environment, to hide himself from the prey. Chameleon is also like any cold-blooded reptile, like snakes, very cold. So actually chameleon have these properties to be invisible in the infrared, which is very handy, because lots of nocturnal animals, like cats, are tuned, can see in the infrared. So they are invisible during the night as well to those animals. So infrared is actually corresponding to heat. So if I take the picture of the light bulb within infrared, it's emitting heat, so it will be very bright as well. And actually, there is far more than that. If you go to the other side, like I mentioned already, you go for a very higher energy light that our eye can see. It's called ultraviolet. And there is a full spectrum of light. So this is the part that we know, the visible light, because we can see it. But actually, light can take very, very many different forms. It's going from the radio. So by definition, you always refer radio to the ears, but actually radio is not related to the ears. Radio is light. Very, very long wavelength light. So the radio we're using less and less, but the radio systems for listening to radio, it's actually how you communicate between one emitter and your receptor is done with light. It's called radio light. I also have a very famous microwave light you use every day when you heat up your breakfast in the microwave. So it's using emitting light. So the microwave oven is emitting light in the microwave wavelength, which has the properties to excite very much the water molecules and heat it up your food or your water. Then you have the infrared we mentioned, the visible light, the ultraviolet. We have X-ray. X-ray is a form of light. So you're all familiar with X-ray. One of the properties of X-ray, so it's very high energy. You know that X-ray are dangerous. So it's very high energy, and one property is it's going through flesh, but it's reflected by bones. So bones are very dense, so they stop X-rays. But flesh is very soft, so X-rays can go through it. That's why we use X-ray light when we go to see the doctor to check if you have a broken bone. It's just stripping up from your flesh, and you see only the bones. And then we have something that we call the gamma rays, so very energetic things. So all those different properties of light have different frequency or wavelength. So I mentioned radio are very long wavelength, while gamma rays are very, very short wavelength. Visible is there. So wavelengths, usually we measure it in meters or nanometers. Nanometers 10 to the minus 6. So this is a visible light is between 10 to the minus 5 and 10 to the minus 7. And just to give you an idea, the wavelength going from radio to something like 10 kilometers to the gamma rays 10 to the minus 14. And this is corresponding to the scale of things that we know. So 10 kilometers, so the wavelength of radio correspond to the size of the Mount Everest. 10 to the 2, so 100 meters correspond more or less to the size of skyscrapers, like the 101. 1 meter, so in radio, correspond to the size of human beings. Then infrared would be the size of fingernail to pinhead. And actually visible lights, we are talking about the size of dust, bacteria, viruses, and here we are just going down to the atom era. So very, very short. So the spectrum is taking a very wide range of wavelengths to which correspond different energies. So radio are very low energy, and gamma ray very, very, very high energy. So what is light? Once again, this is a very, very difficult question, and lots of very clever people have worked on it, including geniuses like Einstein, and the solution is not very easy to understand. So I have described light as a wave so far. So we know that light has a property of waves. We can measure the wavelength and convert the wavelength into energy. But actually, you probably all heard about the terms photons. So light also is a particle. So it's nor wave or particle, it's both at the same time. And we have lots of experiences that demonstrate this is the case. If you take a very, 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 very short shutter snapshot of a source of light, you will see it's coming as particle, as photons. It's something that has been demonstrated since many years now. So we can break up light into particles that we call photons. And each photons carry an energy. So the higher the frequency, or smaller the wavelength is, the higher the energy of the photon is. So I told you wavelengths correspond to energy. Actually, we can see it that packet of wave called photons, and they carry energy. So if you have very short wavelength, you have photons with very high energy. So the energy corresponds to wavelength, so it corresponds to the colors. Be careful, it doesn't correspond to what we call intensity. So intensity is the amount of light you receive in total. It's not linked to the energy of the photons. Okay? Intensity is number of photons you receive in total. Energy is the quantity related to the frequency of the wavelength. It's the quantity stuck in one photon. It's exactly like you can imagine the energy of an iron ball and a baseball. The weight is totally different. It's stored into the ball, but the intensity corresponds to the speed at which I will throw the ball. So, what is light? So now, in terms of mathematics and physics, we start to have a very precise answer. It's complete, but actually, for the main part of the people, including physicists, it's rather confusing. And the problem is, it involves very complicated physics, called quantum physics. And I will give you a snapshot of it a bit later today. So, what you have to realize is light is totally different from anything else we know. It really can't relate to anything that you know really. So I will use metaphors. I will use things to explain to you what it is, but it's not exactly that. So when I talk about baseballs or things like that, don't think that photons are like baseballs. There's something different. It's just to try to explain myself a bit clearer. So light will act sometimes like waves, like exactly a ripple in the pond. So if you're nearby a pond with fishes and you throw a rock into it, you will see the wave propagating. So light will have this kind of properties, propagating like waves. Also, once again, it's just an analogy because unlike sound, so you know that sound is actually what's happening when I speak to you is my vocal cords are vibrating because of the air going through my throat. And vibration is propagating through air. So what's happening is that the molecules of air are compressed and depressed. So I'm propagating a wave. It's going to your ear. And in your ear, it's vibrating your tympan. And then it's transferring to electric wave to your brain. So sound is propagating through the air. If you go to the space where there's no air, you can scream as much as you want. No one will hear you. This is Alien. You've seen the first Alien movie. That was the title. In space, no one can hear you scream. That's true. But light propagates through no medium. There has been a long list of problems for a very long time. People never really understand the properties of light. Newton was thinking that there is something called ether for which light is propagating. But actually, no. Light's propagating through nothing. It's just a wave going through a void. Emptiness, nothing. Actually, the properties of wavelengths of light depend on the medium. So usually when we say that the speed of light is 300,000 kilometers per second, what we should add is in void, when you don't have anything. But the speed of light changes actually with the medium. So I'll show you the example of glass. Speed of light change with when it's propagating through glass. But if you go to a swimming pool or go to the sea, you will see that light speed will change with the properties of the medium. if you go to the sea, or if you put your feet into a swimming pool, and you look at your feet, you will realize that your legs look very shorter. If you do the experiment next time you go to a swimming pool, and next time you go to the sea, you look at your feet, and you have the impression that suddenly you're a midget. You have your feet that are here. And this is due to the properties of propagation of light in water, which are different from the properties of propagation of light in the air. But light doesn't need any of this to propagate. Also, light can act like a particle sometimes. And it can knock other particles like electrons in atoms. So a given photon will go through, if you have an atom, will go knock the atom and change its properties, exactly like a ball. So if you do many experiments, lots of different experiments are showing that duality of light exists. It has sometimes the properties of wave, sometimes the properties of particles, which make it very weird. And the behavior of light is generally totally random. So let's go back to these notions. So first, let's go to the notion of waves. This is the example I gave to you. You take, for instance, here, it's an apparatus where you have water and a little system that is tipping the water like that at a given period of time. So every second, for instance, dipping into water. And what you can see, it's creating waves, circular waves from the center. And those waves are propagating at a given speed. So we can define, if you go very far away from this apparatus, okay, the radius is very big, so it looks like they are parallel. And the difference between two crisps is called the wavelength, lambda. And the inverse of the wavelength, or lambda here, is what we call the frequency. So wavelength is the difference between two crisps, and frequency is the time it's taking from one crisp to come to me to the next one. So wave consists of peaks and troughs, and wavelength is the distance from one peak to another, to the next one. And frequency is the number of peaks passing by any point at each second. So this wavelength is propagating to a given speed. So it depends on what we're talking about. Sound is propagating at the order of 300 meters per second. Speed is how quick the wavelength is moving. So 300,000 kilometers per second for light. So if you take the wavelength and you multiply by the frequency, you got the speed. So wavelength multiplied by frequency is speed. In other words, wavelength is the speed divided by the frequency, or the frequency is the speed divided by the wavelength. So this will be measured in meter, this will be measured of inverse of second, and this will be measured in meter per second. So light is a very peculiar kind of wave. It's what we call an electromagnetic wave. So electromagnetisms, you're familiar with electricity, you're using it all the time, and magnetisms, if you put a magnet on top of your fridge, you know what magnetism is. Actually, those two things are very intrinsically coupled. It's demonstrated since a very long time. So for instance, if you take this kind of apparatus here, so this is a cable, copper cable, it's rolled up like that, and this is a magnet, like a magnet you put on your fridge. And if you take this magnet and make it move through this wire cable very fast, you will generate electricity into the cable, and you can measure it. And the other way around, if I take this solenoid, this wire is rolled up like that, and input electricity into it, inside I will create a magnetic current, a magnetic field. So this is things that are known very long, since a very long time. I don't want to enter too much into details, but remember that light is actually an electromagnetic wave. And it's propagating at the speed that is very well known, the speed of light, 300,000 kilometers per second. So for light, you can relate the wavelength and the frequency through the speed of light. Once again, this is the speed of light in void. So this number change according to the medium. So I don't want to enter too much into details, but remember that the coupling between magnetic and electric fields is creating actually light. This is something that has been demonstrated by Maxwell in the 19th century. Okay, so let's go back to our electromagnetic spectrum. So we know that the speed of light is 300,000 kilometers per second. We have many ways to measure it. If you're interested, I can describe you different experiments that can be made to measure the speed of light. And you can relate frequency and wavelength through the speed of light. So here we have the wavelengths, okay, once again, from gamma ray to radio. So wavelength is bigger and smaller in gamma rays. Visible light is here. Frequency, of course, is the opposite. And actually, we can relate it to energy. I'll show you in a second how you do that. So when the wavelength is increasing, frequency is decreasing, and energy is actually decreasing. Usually, wavelength of light are measured in unit of nanometer, it's 10 to the minus 9 meter, of angstrom, it's 10 to the minus 10. So angstrom is this symbol with a circle on the top of the A. Angstrom was the Danish physicist, actually. So 1 angstrom corresponds to 0.1 nanometer. And usually visible light has a wavelength between 4,000 angstrom and 7,000 angstrom, or 400 to 700 nanometer. So this is the way we're measuring visible light. Of course, when we're talking about radio, we'll talk about millimeter or meter. And as I told you that light is also a particle. So you can relate this wave to a given particle of a given energy. And we have a way to relate the wavelength or frequency to the energy. And it's coming from the quantum definition of light. And I can't have the time to explain to you exactly how it comes. But remember that we can relate the wavelengths, the wave properties of the light, to actually the energy stored in the photon. So this particle, in which storing the energy of light, is called a photon. For instance, if you want to explain what we call the photoelectric effect, or piezoelectric effect, any detectors that is sensitive to light is transforming actually light to electrons. So this is an effect that gave Albert Einstein his Nobel Prize. So you know that you have all those detectors for light. Any detector for light is actually using the properties of particles of light. So photons store a specific energy, that's capital E. This is proportional to the frequency using this equation. Energy equals H. So H, it's called the Planck constant, after Planck, who discovered it. This is linked to the, once again, quantum properties of matter, times the frequency. Or, because we know that the frequency is the speed of light divided by the wavelength, so E equals hc over lambda. H is this number in joule second. Be careful, not joule per second, joule second. And the speed of light is around 300,000 kilometers per second. So usually, the energy is the unit in which we measure the energy is in joule, or electron volt for very tiny energy. So 1 electron volt is 1.6 10 to the minus 19 joule. So it's a very, very little quantity of energy. Be careful, I already mentioned that the energy of a photon does not depend on the intensity of the light. It's the energy stored in one photon. The intensity of the light is actually counting how many photons are received. So it's totally independent. So this is more or less the definition of the light as wave and particles. And following those two different approaches, we can explain many different properties of the light. So I will start to list the properties of the light, and I will focus on the properties that are very useful for astronomy. And there are 4 of them: transmission, dispersion, reflection, refraction. So this is the same story when you have a beam of light here, a prism of glass, and it's spreading through the rainbow. I showed you. So the fact that the light is going through the medium is what we call transmission. It's going through the medium. The fact that the light is spreading the rainbow colors is what we call dispersion. Here you see that actually the light, part of the light is reflecting. That's something that you use all the time in mirrors every morning when you brush your teeth. You see your picture, it's because the light is reflecting in the mirror. So here you have part of the light that is reflected by the surface, part of the light that is transmitted. And also you can see that there are actually as well here part of the light that is refracted. So these are 4 different properties of light that can be explained here, and I come back into details. And they're all very, very useful for astronomers. So the transmission is that the portion of light is traveled through a medium. The dispersion is the light is spread out through the medium. The reflection is light that reflects at an angle equal to its index angle. I come back on that. And what we call refraction is the path of light change with the medium. So reflection. Reflection is used by mirrors and is the base of optical astronomy. Actually, it's the base of astronomy. So there's something that you're very familiar as well, because many of you are wearing glasses. So we're using the properties of light to modify your view. So the reflection part. So light that hits a mirror is reflected at the same angle from the incidence from. So if you have a flat mirror, okay, light is reflected perpendicular to it, so it's going flat to you. But if you go to any funny fair to have fun, you have seen all those deformed mirrors that give you very weird projection of yourself. Mirror like that are making you very tall. You can have mirrors that are very deformed and make you tall and small at the same time. You have all seen this kind of example. And these are different properties of the light, of the reflection of the light. And Newton demonstrates that it's a very simple way. Actually, if you have a beam of light coming to a mirror here, so this is locally where the mirror is flat, this is perpendicular to the mirror, then the light will bounce back with the same angle. So the angle I and R are the same. So if I take a mirror like that, light will reflect the same way, same angle compared to the norm. So if you take a mirror that is designed with a parabola shape, this kind of shape here, what happens is the light here is reflecting perpendicular, so it's going down there. The light here is reflecting with the same angle compared to the perpendicular, it's going there. The light here, the perpendicular is here, light is going there, etc. So what this kind of mirrors are doing is they're concentrating all the light in one given point. It's called a focal point. So you can use that for telescopes, but you can do that for oven. So there are solar ovens, for instance. Because you're concentrating all the light here, it's going to be very, very intense. So it's going to be very, very hot. So if you put your chicken in the middle of there, if you have a bigger one and it's a very sunny day, then you have a cooked chicken after a while. So the idea is to focus all the rays in the same place. It's very important, and we'll see when we will talk about the refraction and dispersion. It's also very important, for instance, to see further. I'll explain to that in a minute. Another property of light is refraction. That the fact that light travel at different speed in the different medium. So for instance, the speed of light in vacuum, in void, is 300,000 kilometers per second. But in air and glass, it will be different. It will travel at different speed. So for instance, when light hits the material at an angle, part of it slows down while the rest continue at the original speed. It's a result of change of direction. So for instance, if you have a beam of light going to the glass here, so you're entering the glass, and actually given the difference between the speed of light in the vacuum, in the air, and the speed of light in the glass, it will slow down in the glass because it's more dense, and so it will have a result of an angle. And once again, when it goes from the glass to the air, it will change again angle. So this is the deflection. So you have one refraction when the light is entering the glass, another refraction when the light is entering the air. And actually we can demonstrate that the deflection angle is linked to the amount of medium that the light is crossing. So you can relate how much glass the light is traveling through to this angle. And another properties of light is that, I mentioned that, different colors or different wavelengths will have different speed in the different medium. So in that case, when you go through glass, the speed of red light will be slower to the speed of blue light. That means that the red will be more deflected than the blue. So we end up here with different colors having different deflection angles, and then we end up with a rainbow. A very, very commonly used properties of refraction is actually lenses. So what lenses are doing is that if you design a piece of glass that has this parabolic shape, this very peculiar shape, what you will do is that for all the light is initially incidented perpendicular, you will focus all the light in one point. The same way that the reflection will work, that means that here this light is entering and slightly deviated, but the angle here, so the amount of material that is crossed by the light is smaller here than here, so the deviation will be bigger than here. And if you go through the lenses, here you have two things that are parallel, so it will go straight. And here, this angle will be very big compared to here. So you will have a lot of refraction. So this is something that you are commonly used with glasses. You know that actually a cornea in the eye is exactly like that. It's a lens. So it's what the cornea is doing is focusing all the light I can see in my views angle to a point behind it in the eye, which is called the retina, which is the detector to which we can measure, we can detect light. And sometimes the cornea is slightly defected, so you need to add an extra correction. So you add lens in front of it. All the people that are wearing glasses or contact lenses are using this effect. Of course, astronomy, we're using that a lot. Okay, we're concentrating all the light in one point. So why is it interesting for astronomers to concentrate all the light in one point? There's something that is very faint, so emitting very little light. You take all the light possible and focus it on one point, so you will magnify it. You will catch up more light. So this is a way of concentrating all the light in one point. This is more efficient to detect faint objects. Do you have any questions about that? You understand the principles, right? It's not too difficult. So those two, reflection and refraction, are the base of telescopes. So next week we'll discuss about telescopes. I'll describe that in more details. All the telescopes are using this kind of phenomena. There is another property of light that is extremely interesting, is the fact that light spread differently in different medium. So let's take an experiment that's called the Kirchhoff experiments, after Kirchhoff. So you take, for instance, a hot light source, which is emitting white light, okay? And the light is going, first of all, through a prism. So the light is spread, and you will have the rainbow. But actually, this rainbow is called the continuum spectrum. So you have all the light presented, all the wavelengths are there. But different sources, by experiment, will receive different amount of light according to different wavelengths. So for instance, in that case, the source will emit more light in the blue here than it does in the red. It's not related to energy, it's related to the intensity. The number of photons, blue photons, emitted by this source is higher than the number of red photons. So if you look at the intensity, that means the amount of photons received per wavelength, and you trace it, so this is amount intensity versus wavelength, you will have a curve like that. Here you have more light than here. Alright? So every source actually doesn't emit the same amount of light according to the wavelength. Come back on that in a minute, but for instance, I told you that human body, is emitting heat. Actually, we're emitting a lot of light in the infrared, but very little light in the optical. We're emitting this kind of spectrum, continuous spectrum, but the peak here is in the infrared. And it's dropping very rapidly in the optical. That means that if you switch off the light, nobody of you will be visible. But if I use an infrared detector, I will see all of you. Let's complicate it a bit more, the thing, and take the hot light and put in between the hot light and the prism, the hot source and the prism, a thin cloud of gas that is cooler than my source. So gas composed of given body, let's say hydrogen or water. So you take a gas of hydrogen and you put it between the source of light and your prism. And what you observe in your spectrum, so you still have the continuum spectrum from the light, but what you observe is dark fringes in there. You have part of the wavelength spectrum that have disappeared. That means that light is stopped somehow in the cloud of gas at very precise wavelength. So if you count the amount of light received per wavelength and you plot it in the same diagram here, intensity versus wavelength, you will have the continuum spectrum, but you will have holes in it. At very precise wavelengths, you will have less light than you should have if you didn't have the gas. And if you put another prism that is not in the path of the light, original light, and you do a measurement, you will have another spectrum, which is called emission spectrum. This is called an absorption spectrum, and this is called an emission spectrum. Yet what you will see is that actually your gas is emitting light. but at very, very precise wavelength only. So it doesn't have a continuum spectrum, but it will emit light at very precise wavelength, which corresponds exactly to the absorption spectrum. So what's happening is my gas, when the light is going through it, is keeping some photons for himself, and then is re-emitting it by himself. So if you look at the light compared to here and here, you will see that there are photons missing that were kept by the gas. But if you look at the cloud of gas later, it will re-emit those photons. So these are called the Kirchhoff's laws of radiation. So the first law is the continuum spectrum. So if you take solid or liquid or dense gas excited to emit light, it will radiate at all wavelengths and thus produce a continuum spectrum. So you will have all wavelengths but with different intensities. And then the second law is the emission spectrum. If you take a low density gas that is excited to emit light, and it will do so at specific wavelength and then produce an emission spectrum. And the third law is the absorption spectrum. If light comprising a continuum spectrum passes through a cool low density gas, the result would be an absorption spectrum. Okay, so the continuous spectrum, you have a light bulb, you're going through your telescope, you have a spectrograph, this is just a prism that's spreading the light, and you got the continuous spectrum. And the continuous spectrum have different properties, and very interesting properties actually. Is that different things, different objects, will emit different continuous spectrum. And they all have the same shape that we call a black body shape, this bell shape here. So this is the intensity, the amount of light that is emitted versus the wavelengths. Here this is ultraviolet and infrared. And actually the peak of intensity, where we have the maximum of light in this spectrum, corresponds to the temperature of the body. So if you take a star that is very, very hot, 15,000 degrees, very hot star, it will emit the peak of its light in ultraviolet. The sun, it's around 5,800 Kelvin degrees. It emits its peak of light in the visible lights. That's why actually our eyes are tuned for it during the day. So this is where the maximum of light the sun is emitted. But you see that the sun is emitting ultraviolet, you know that, sun cream, and infrared as well. And if you take a normally constituted human, the peak of its density is around 300 Kelvin, correspond to our temperature, 37 degrees. And we are emitting in the infrared. So human bodies are actually black bodies. We're emitting light as well, according to the same law. So there is a direct relationship between how hot the stuff is and where the peak of the continuous emission is. It's called the black body radiation. So a black body, that's something that absorbs all electromagnetic radiation, or something that irradiates thermal radiation temperature. It's what we call a black body. So now, that said, if you take a piece of iron and heat it up with different temperature, and you look, the iron glows red, yellow, or white. What is the hotter? Red, yellow, or white? Nobody knows? If I give you the choice, I take a piece of iron, I heat it up, and I want to burn you, which color do you prefer? You prefer white. You're wrong. It's hotter. White light is very, very, very... White light, heated to white, it's extremely hot. Far hotter than red. Actually, red is pretty okay. You can see it when you have a flame. The flame, when you use the gas, for instance, and you look at the flame, and you put your pan in it, you will see the center of the flame is blue. The butane is very blue. It's actually where it's the hotter. But on the border of the flame, it would be yellow or orange. It's actually where it's the cooler. So when you go to blue or white, it's very hot. Red is cool. Right, it's coming back to the same idea. Blue, the black body peaks at very high temperature, so blue light is very hot. Red, the black body is peaking at lower temperature, so red is less hot. And actually, human body is emitting in the infrared, so it's very cool, 37 degrees. So we have two laws. For the purpose of the homework, you can use it, but I don't want to remember really the laws, but they are called Stefan Boltzmann law and Wien's laws. So the Stefan-Boltzmann's laws tells you that the luminosity, the amount of light that is emitting, is proportionate to the temperature to the fourth. So what it does in real words is a hot body is brighter than a cool one. You see? There is more light in blue than the red. So if you take something very hot, it will be brighter than something that is less hot. And the second law, Wien's law, is saying that the hot body spectrum is bluer than the cool one. So the peak here, 15,000, is bluer than the peak here at 500,000. So in mathematics, you wrote it that the wavelength maximum is proportionate to the inverse of the temperature. Okay, so we come back to those three definitions that you have to be careful of, is energy, luminosity, and temperature. So, Stefan-Boltzmann law, energy is proportionate to the temperature to the fourth. E is the energy emitted per surface area per second. That means the amount of energy that you receive in a given area per given amount of time. T is the temperature in Kelvin. So T to the fourth is T times T times T times T. And sigma is what we call the Stefan-Boltzmann constant. So you can relate energy, total energy, with the temperature. In words, that means that hot stuff glows more. And what we call luminosity, okay, is the total of energy emitted per second. You can relate, actually, the luminosity to the energy. So take an area. So you take a circle area of a radius r, and 4 pi times r squared gives you the total area covered. And this is E, this is the energy. So the luminosity is 4 pi r squared. It means the surface of what I'm measuring, this surface here, times the energy. So you can include sigma t squared. Okay? So pi in that case is 3.14.156, and r is the radius of the body. So what does that mean is that bigger and hotter stuff glows more. If you take a small ball or a big ball, for the same amount of energy, the big ball will be brighter. So I don't want you to remember any of this. You probably have to use it for the homework, but in general, forget about the equations. But remember that. Hot stuff glows more, and bigger and hotter stuff glows more. And this will talk about that in details when we go back to stars. I'll show you that actually big stars are more luminous than small stars. So, emission spectrum. So what's going on there for emission and absorption? So it looks like, as you look at the spectrum and the fringes are corresponding exactly, it looks like it's the general property of the light. So those fringes are exactly corresponding. So there's something happening. And actually, this property of light entitle us to trace matter, the composition of matter. That is rather important. And actually you all know, you all use this property of matter every day. So here I have a blue sweatshirt, there I have white then, a brown there, there's some yellow there, red. All those colors we're looking at, it's actually linked to exactly the same properties. So, and colors of stars and spectrum of stars, you can get some spectrum of different stars here. I can show here different stars, and as you can see, they have different fringes, different absorption lines. So if we understand well those absorption lines, this is linked completely, directly to the composition of the star, of the element you're looking at. So if you know exactly where those lines are, you can know what is composing your star. So the spectra of star is more complicated than the pure black body spectra. It has those lines. And to really understand what those lines are, we need to understand the atomic structure and the interaction between light and matter. So it's very complex matter, and it can go very, very complex. But there is a simple way of looking at it. And first person to explain this kind of phenomena was actually Bohr with his atom description. So this time I make it right. Bohr was Danish, right? Armstrong, I mentioned Armstrong is not Danish like I said last week, it's Swedish. Thank you. So Niels Bohr came up with this description of the atom. So you know probably that atoms are composed by electrons orbiting a nucleus. So the main part of the mass of your atom is inside the nucleus, packed in the nucleus. The electrons is very, very small, very light, and the way Bohr described it is that you have a very massive nucleus composed of protons and neutrons, and around this there is a cloud of electrons orbiting around it. So it's not gravity acting here, it's electromagnetism, because this is charged positively and this is charged negatively. So it's exactly like the magnet effect. So the electron is attracted by the positive charge, and it's just orbiting around this nucleus. Nowadays we have even more complex description, but this is a rather simplified description, and it helps to understand what's happening. So this is another way of describing it. You have the nucleus here, and electrons. Let's say this is the case of the hydrogen atom. So hydrogen atom is the simplest atom that we have. It's only have nucleus and one single electron. If you go for more heavy elements, you will have more and more electrons. Oxygen typically have 16 electrons, etc. So let's take the example of a hydrogen atom. So a hydrogen atom is composed at the center of a nucleus, and then one electron orbiting around it. And the distance between the nucleus and the electron is quantified. This is what we call quantum theory. The electrons can't be anywhere I want. It's not totally true, but let's simplify it. The electrons can't be anywhere he wants. He only can live in different regions away from the nucleus. It's quantified. And each region corresponds to a level of energy. So here, when the electron is very at the lower bottom region, it's closer to the atom, and actually this is very cool for him. He doesn't need to have too much energy. It's just like you when you're in bed. So this is his home. So level 1 is the electron's home. But if something happened, he gets excited, he had to go to work, or he goes to party with his friends, he will go for higher energy levels. Can go to level 2 and level 3. And he's jumping from one state to another. On the other hand, you can see like a step. When you have the lower level, and then you need to go to the next step. Higher level, next step, etc. It's not continuous, it's a step function. And actually, this different steps, is like different levels, requires different amount of energy. And once again, it's quantified. We know exactly what amount of energy you need to go from that step to this step. And as this scheme show you, the difference of energy is getting smaller and smaller and smaller. So it's very difficult for the electrons to jump from level 1 to 2, exactly like it's very difficult for any of us to get up out of our bed in the morning. Okay? Then it's getting easier to go further and further. And of course the electron can jump one way or the other. So what's happening if I take my hydrogen and I just throw to it a photon? You remember? Photons, quantum of light, they have a given energy. So what happens if the energy of my photon, and remember energy of photon corresponds to a frequency or a wavelength. So what happens if the energy in my photon corresponds exactly to energy for my electron to go from one step to another, one level to another? Well, it's exactly what you guess, is that if I take a photon and throw it on my electrons, on my atom of hydrogen, my electron will catch it, and if the energy corresponds exactly for him to jump from 1 to 2, then he will do the jump. So if I take a photon, launch it of my hydrogen atom, then my electron will jump one level. And if the energy is far bigger, and but correspond, let's say, to the amount of energy required to jump from 1 to 4, then the electron will do so. So this is what happens actually in absorption. You take a cloud of gas of hydrogen, and you send some light into it, and all the light that correspond to the energy required to jump from one step to another will be absorbed by the gas. That's why you have the fridge. Okay? On the other way around, let's say that you have gas that is excited. That means that the electron is not living anymore at rest, but it's higher level. And you let it rest, let it, let's say, cool down or live its own life. The electrons is like us, it prefer to be in bed. So eventually, it will jump back. And by doing that, it doesn't need this energy anymore. So it will release the photon. So you will emit a photon at the given wavelength. So we have the emission line. So there are very famous lines from hydrogen called the Balmer line. So usually there are lines for higher transition. So when we'll talk about astronomy in general, I will come back and talk about H alpha, H beta, H gamma. These are hydrogen lines or Balmer line corresponding to the jump between level 2 and 3, 2 and 4, and 2 and 5. And for the jump between 1 and 2, 1 and 3, 1 and 4, and 1 and 5, it's called Raman lines. So when we talk about Balmer lines, usually that's what we mention. So just to summarize, if you have an atom at rest and you just throw a photon of a given energy, but this energy doesn't correspond to any energy level for the electron to jump, then nothing will happen. The photon will just go by and nothing will happen. But if the energy of the photon corresponds exactly for the atom to jump from one level to another, then we will absorb. It will absorb the photon. That means you will have a black line in your spectrum. And then you have what we call ionized atom, ionized gas. And after a while, because electrons don't like to remain too long in higher quantum states, so the electron will jump back to the ground level and emit back the photon. So another way to represent those steps is those lines. So you have level 1, level 2, 3, 4, 5, and you see that when you go the higher, the smaller energy you need. And we know now, from experiments in the lab, how much energy is needed for an electron to jump from one level to another. For instance, from level 1 to 2, it's 121.6 nanometer. Energy corresponds to 121.6 nanometer. Okay? And if you're more interested in those levels here, okay, so these are the Balmer. From 6 to 2, it's 410. From 5 to 2, it's 430. From 4 to 2, it's 486. And from 3 to 2, it's 656. So if you take the emission absorption spectrum of a gas, so when it's ionized gas, what you get is the emission at the wavelengths corresponding to those levels, 410 to 656, it's the H alpha. And on the other way around, if you take the spectrum of a source for which the light went through a gas, what you get is the absorption lines at the same wavelength. So now, if I take the spectrum of many different gases or phases, then I got different spectrum in emission and absorption at the same, right? So I got helium here with those lines here, sodium, double line here, neon, and then this is the spectrum of a star, for instance. So then you will have all the lines corresponding to different molecules. So here hydrogen lines, here you have oxygen, helium here, etc. So those things will add up at some point. If you take a spectrum of a star, for instance, you have the black body and you have all those absorption lines, and by comparing with the spectrum coming from the lab, from different elements, you can match it and deduce what is composing your star. So this is a very, very important property of light. And once again, you use it every day. Colors are exactly coming from that. He has a blue sweatshirt because the matter, the molecule of dye that is composing his t-shirt, are emitting all the light except the blue. So what is re-emitted is only blue. Same thing with white. So white is re-emitting all the light, disregarding its color, and black is absorbing all the light. That's why you know that when it's hot outside, it's better to wear white colors or bright colors, and when it's cold, it's better to wear black. Everyone knows that. So black absorbs energy, black absorbs light. So the last property I want to discuss with you is also very important. So far we have seen that thanks to light, we can modify the path of light, and we'll come back with the telescopes, very important because it helps us to magnify. So you know when you're using glasses or googles, you can see further. So this is coming from the refraction and reflection properties of light. So we'll come back in more detail in a minute. And we know that thanks to light, we can also describe the content, what is composing the object you're looking at, which is could be a star or a galaxy or a planet. So we can describe what is composing those different objects. Another very important property is the Doppler shift. This is something that you actually know very well. Doppler effect. Every morning when you're walking to catch the bus and you have scooters passing by you, you know perfectly well. Same thing with, for instance, police cars, the sound of the police cars. It's not the same sound when it's coming on your back, and the sound is varying when it's passing you. You know, it's doing something. Meow. Okay? This is not the car changing its sound. It's actually the sound, the fact that the car is doing faster than you, is changing the property of sound. So the whistles or the car whizzing passing you is what we call the Doppler shift. And actually Doppler shift happens with sound. I'll explain to you a bit more detail what happens. But it happens also with light. So actually what happens is an object that is moving toward us will be bluer, and an object that is moving away from us will be redder. Of course, you have to go pretty fast. So if I go further closer to you, I won't be bluer because I'm not running fast enough. But if you're approaching the speed, very high speed, close to the speed of light, this is a visible effect, measurable. And if I run away from you, I won't be red neither. Actually, I will be red because I will be out of breath, but this is a different problem. So a source that is moving towards you, the light is blue shifted. You can see it like the photons are more energetic. It's going towards you, so they're gaining energy. And a source that is moving away from you, the light is red shifted. You can see it like the photons are less energetic. Remember, the speed of the photons doesn't change. It's always the speed of light. So, let's go back and I'll show you a scheme to explain this a bit better. Let's take the example of this train that is emitting sound. Okay, so sound is a wave. So if you are behind or before the train and the train is not moving, you hear exactly the same sound. But now, if the sound is moving away, what's happening is that the wavelength, the sound emitted towards you, it's coming towards you, is getting shorter. It's compressed because the sound, the train is moving that direction. So you have shorter wavelength, which is emitting a more pitchy sound. And if you're behind it, the wavelengths will be longer. They are stretched because of the speed of the train. So you get less lower pitched sound. So it's going from high to low when you hear. And this is a very well understood phenomena. And we have exactly the same thing happening with light, but this velocity needs to be very high. Okay? So if the source of light is moving fast away from that guy will see it bluer than it is in reality, and this guy will see it redder than it is in reality. And the relationship between the velocity of the object and the difference of frequency or wavelength is very well known. It's the ratio between the velocity of the object and the speed of light is equals to the difference of wavelengths divided by the wavelengths at rest. This is the Doppler shift. And this works only if the velocity is very high, but also if the velocity is far below the speed of light. Then we are entering another realm when your velocity is close to the speed of light. So if your velocity is too small, that means me running towards you, there will be a difference, but it will be so small that you won't be able to notice it. That's what it's saying. So, in practice, a Doppler shift, you have a spectrum, emission spectrum coming from a gas. At rest, you know where the wavelengths are. And if my object, my gas, is moving away from you, you will see a shift towards the blue. So this line will be here, this line, green line, will be shifted towards here, and this red line will be shifted redder. And if the redshift is greater, that means if the object is moving even faster, then those lines will get even redder. And the other way around, compared to rest, if the object is moving towards us, the lines will go bluer. And if it's faster, it's getting even bluer. So you see it coming. This is very, very efficient way to measure velocities. So for instance, if I want to measure, I have two objects on my line of sight, and one is moving away from us. Let's say that they're rotating, orbiting one around the other. Then one object would be redder, and the other would be bluer. And we'll be able to measure it. And then you can measure the relative velocity of those two objects. So when we talk about binary stars or exoplanets, planets orbiting around other stars, this is one way to measure their velocity. And if you're a bit aware of gravity, Newton's laws, you know that how fast an object is rotating around the other is directly linked to the ratio of mass. So we can derive the mass of the planet like that. We can go for something even more complicated. Imagine that you have a bubble of gas in the space and you measure through, because it's gas, so you can measure through it. You will have a component that is getting redder and a component that is going bluer. So you can measure the velocity, how fast the bubble of gas is expanding. Something we're measuring in star-forming regions, etc., etc. So Doppler shift, Doppler effect is extremely important in astronomy. And I will mention it many, many times during the lectures. So, as a summary, well, when you measure the spectrum of a star, you get the black body that's giving you its surface temperature. You get the absorption spectrum that it gives you the composition, and you may get some Doppler shift effect if your object is turning, for instance, rotating. And if you look, I showed you that last week, if you look at the spectrum of a sun, you see that it's extremely complex. So this is from red to blue, so it's only in the visible, and all those different lines, and sometimes they are superposing, you see there are very broad lines here. All those different lines correspond to different elements. So it's exactly like cracking a code. So if you decipher this code, you know exactly what is composing the star. And actually some of those elements may be also shifted due to velocity, so you can differentiate where the element is within the star. So we can go very, very detailed study of it.